Okay, so today's lesson we're looking at alkenes. Now alkenes are another hydrocarbon molecule. It's another family of molecules. In fact, it's a homologous series. So we've already looked at alkanes and looked at the homologous series of alkanes, which were all single bonded hydrocarbon molecules. And we're now going to look at the family of alkenes. They're hydrocarbon molecules, so they only contain carbon and hydrogen. Now this is our first molecule. This is ethene. Now if you remember, when we were naming the alkanes, we knew that it was an alkane because it had ane at the end of the name. Well, in this case we know that we've got an alkene because we have ene at the end of the name. You'll also notice that we're starting with eth, and the eth is the prefix for when we've got two carbons. Now the reason for this is because the difference between alkanes, where they're all single bonded, and alkenes is that alkenes have at least one double covalent bond. And you can see this, I'm actually going to highlight in red for you on the molecule, these two bonds, that's a double bond, and that's between the two carbons. There are two bonds holding those carbons together. Interesting features that this molecule has is that it can no longer rotate around that bond. Those two bonds hold it very rigid in the shape that it's in. Now, these two bonds also mean that it's going to be a little bit more reactive. Importantly, when we're looking at alkenes, you don't need to have more than one double bond for it to be an alkene. You can have multiple double bonds, but usually when we're looking at GCSE level, we're only interested in one double bond in the entire molecule. And because hydrogens can only make one bond, it's going to be a double bond between the carbons. So if I draw this molecule out the same way as I drew out the alkanes, and I'm going to draw, there's my carbon with the bonds between, and again I'm going to draw my single covalent bonds going out to my hydrogens. Now this isn't actually showing the displayed formula, it's just a way of representing in 2 dimensions that 3-dimensional shape. And it's just a way of showing how the bonds arrange evenly around the carbon. So you'll see that they roughly take up a third of the distance each. Now, if I'm going to draw the displayed formula, I actually need to make sure that I've got the chemical symbols in there. So my displayed formula has got my carbon, I show the double bond still, another carbon, and then I've got the hydrogens. And you notice again, I'm showing the shape as if I've squashed that 2-dimensional model flat on the page. I'm showing how the bonds are laid out, so they're no longer at right angles to each other. You need to know this displayed formula. You also need to be able to recognise the image of the molecule, so the molecular image. I'm just going to remove the red from that image so that you can see that clearly. And you also need to know your molecular formula. So our molecular formula, again, we just count up the number of carbons and the number of hydrogens. So here I've got 2 carbons and I've got 4 hydrogens. Notice where I'm putting the numbers. The numbers must be small and they must be below the line. You will lose marks in your GCSE if you don't put the numbers in this place. If your numbers are not clearly smaller and below the line, they will credit you nothing. It's really important that you are very precise in use of capital letters and in the positioning of numbers in chemistry. Okay, so my next hydrocarbon in the alkene family is propene. Again, noticing that I've got the ene suffix, but I've also got the prop, which tells me that there's 3, and you'll notice that there are 3 carbons. Those are the the black circles, there are 3 carbons in this molecule. You'll also notice that there is only the one double bond. So here there's my double bond. The other carbons are joined together by a single bond. This is normal in alkenes, so you don't need to have all of the bonds as double bonds. So when we draw out our displayed formula, first of all I'm going to squash it flat onto the page. So I've got my double bond between those carbons there, then I've got a single bond, and then I'm going to draw out my hydrogens. So I always make sure that I'm distributing my hydrogens as evenly as I can. Now obviously for this little carbon in the middle here, I can't easily distribute the bonds and not have other hydrogens clash together. So what I've done is I've kept that as a straight. I tend to keep the carbons in a nice straight line and it makes everything easier to see. But you'll notice that at one end I've got right angles, so here I've got right angles between my hydrogens and the bond between the 2 carbons, and then on the other side I have a larger angle where I'm looking at dividing it into thirds. Okay, so to draw out the displayed formula here, so again the displayed formula, remember, it's got the symbols in it, so I've got my carbons that are joined by the double bond, and then I've got my last carbon. Now you'll notice this is why it's really important when you're looking at alkanes that you always draw the bonds in. Then I'm going to add in my hydrogens around, so I'm replacing the white circles with hydrogens. There's 1 hydrogen attached to this one, and then I've got 2 hydrogens on the end. Now you will notice here that I've put the double bond at one end. I could flip this molecule and have the double bond at the other end, but it will be exactly the same molecule. So it doesn't really matter where the double bond is, as long as the carbon that's on the end that has the double bond has only 2 hydrogens attached and the one in the middle has only 1 hydrogen. This is really important when you're drawing these types of molecules, because when you're drawing these types of molecules, you need to make sure that you're not adding any more than 4 bonds coming out of each carbon. So you'll notice that this carbon here, it's got 1, 2, 3, 4 bonds coming out of it. Here I've got 1, 2, 3, 4 bonds coming out, and here I've got 1, 2, 3, 4 bonds coming out. So that's the best way for you to check that you've drawn your molecule correctly, that you've got no more than 4 bonds coming out of each carbon. We then need our molecular formula, and our molecular formula is C3H6. Okay, so now I've got butene. Again, notice the ene, and that we've got the but, which means 4, so that's for the number of carbons. And I'm going to again highlight for you where the double bond is. Okay, so you'll notice here that I've got 1 double bond, and that's between 2 of the carbons on the end. So I could pick that up and flip it over, so it could end up between those 2 carbons there, but effectively it would be the same molecule. So when we get to this many carbons, we end up with isomers. And this is when we've got the same number of carbons and hydrogens, but the difference is where the double bond is. So let me just pop an example of an isomer for butene up. Okay, so here you can see we've got the same number of carbons, we've got the same number of hydrogens, but our double bond is here in the middle. So I could no longer pick this molecule up and flip it over and have it be the same be the same molecule as the one on the top here. So I'm going to call this one A and I'm going to call this one B. So those are 2 isomers. So these would need chemical bonds to break for them to be the same shape. You wouldn't be able to fit them into the same slot. What we need to do when we're looking at these types of molecules, you do need to be able to draw out one of these isomers. When you're asked to draw butene, it won't matter which one when we're looking at GCSE level. So if we start off with isomer A. So I'm drawing my carbon chain to begin with, always the best place to start, and then I'm drawing my hydrogens around. So I'm just going to add on to the end of each of my bonds here my little hydrogen atoms. So that's the first possibility for drawing butene. The second possibility, if we look at molecule B, so this is isomer B here, is that I've got single bonds, then I've got my double bond, and then I've got another single. And so the way that I would draw this on, I've got 4 hydrogens on each end, and then in the middle, each one of these has got 1 hydrogen. Now, if we look at both of these, you'll notice that they've got the same molecular formula. So whilst the displayed formulae might be different, the molecular formula for each one is C4H8. You can count up those hydrogens and prove this to yourself, but for each of them, it's the same formula. So again, you need to be able to recognise both of the images and both of the displayed formulae as being butene. Okay, so this is our summary of what we've seen. So we've got ethene, we've got propene, and we've got butene. And what you'll notice, the more observant of you will notice that we've started on 2 here. So we haven't got methene. And this is because it's completely impossible to have a double carbon bond if you've only got 1 carbon atom, as you would with meth. Again, we can work out a general formula here. And this you should be able to notice is quite simply that you've got double the number of hydrogens that you do carbons. So our general formula is simply Cn when N is the number of carbons that you've counted, and then we have H2N. So H2N being double the number of carbons. Okay, so in summary, alkenes, they are another hydrocarbon family, and this is again an example of a homologous series. Our alkenes, they contain double covalent bonds between at least 1 pair of carbons. But what's really important is that we're not looking at double bonds between all of the carbons, otherwise we wouldn't have double the number of hydrogens. So it's double covalent bonds somewhere in the molecule. Now this means that our alkenes, they are more reactive than alkanes. We'll come on to this in another lesson. But what this means is that we haven't got the maximum number of hydrogens attached. We could, in theory, break half of that double bond and attach a few more hydrogens. And therefore we say that the molecule is unsaturated. So it is an unsaturated molecule. These, as I've said, they are quite reactive more reactive. And this means that they can be used to make things like plastics. And we also have our general formula, which is CnH2n.